Okay. So in conclusion, forward Euler has a stability region that does not extend to infinity, into the negative infinity, like the original differential equation. And how much does it extend? It depends on delta t. If delta t is small, it extends further. If delta t is large, it doesn't extend as much. Another observation is that here there is a pretty weird region in forward Euler here. Okay, this region is weird because the analytical ODE is stable, but forward Euler I think is not stable. And in particular, if you look at a place on the vertical axis, if you are solving an equation that is exactly imaginary, okay, if you are solving du dt equal to the imaginary number times u, according to Euler's formula, I would be working on circles, right? But forward Euler would not be stable, and that's actually something we didn't really focus on, but we can really observe by looking at our previous lecture. I think this Euler is still the Euler that we use. Yes, identity times this. So instead of having an n list, let's just pick an n that is let's just pick 500 is neither large nor small, right? If we run it, and we can plot our u and axis equal, what we found is that it goes slightly beyond -1, right? It goes beyond -1, which means the magnitude has been increasing. And now if I increase the n by a factor of 10, and I would also increase the time by a factor of 10, if I run it again, and I'm going to plot again, here's what I found, right? So the solution started from 1, it spirals, but it spirals outwards. It's not stable in the long term, right? If I make it 100 times and 100 times, it's gonna be more obvious. I mean, this keeps expanding. I started from here, just spirals outwards, unstable. Again, just like the midpoint scheme, it can be rescued by specifying a smaller delta t, right? The spiraling out pattern is going to be tighter and tighter, but it's ultimately going to be unstable, right? As t goes to infinity, I mean, the solution would go to infinity. Okay, so how about midpoint rule? Last time we solved an equation for which the midpoint rule was terrible, right? Okay, but actually for this particular equation, midpoint is actually fantastic. So let's actually do the same exercise. We choose an n that is we increase the time by a factor of 100, and we increase n also by a factor of 100, so the time is the same. Let's close it, and the midpoint, we run it and plot u. Perfect circle. So midpoint being terrible for the equation we solved last time, for which lambda, if you remember, is -1 plus I, right? But for this equation where lambda is exactly equal to I, midpoint actually solves it extremely well. And why is that? It can also be looked at by the same stability analysis, the eigenvalue stability analysis. I mean, the reason we call it eigenvalue stability analysis is because it depends on lambda, right? And when we have a system of equation, we're going to see pretty soon that lambda is going to be an eigenvalue of a certain matrix. Okay, so the midpoint scheme is we have a uk plus 1 minus uk divided by delta t, no, minus 1 divided by 2 delta t equal to lambda uk. and the iteration would be transformed into u of k plus 1 is equal to u of k minus 1 plus 2 lambda delta t times uk. So now we have an iteration that is no longer one-term recursion. How do we perform analysis of its long-term behavior? We have seen this trick for several times now, right? How do we figure out the long-term behavior of such recursion that involves k minus 1? Yes. Yes, we write this as a matrix system. We write down, we are going to be converting this into a one-term recursion, but of a vector instead of scalar. So is equal to matrix times uk and uk minus 1. Now it's a one-term recursion, right? Okay, and the matrix is going to be what? uk plus 1 is going to be equal to 1 and 2 lambda delta t and 1, 0, right? Okay, so now what is the criterion for this iteration to be stable in the long term? What's the criterion? Yes.
Eigenvalues of that matrix that we have, the real parts of them have to be less than 1.
The eigenvalue of the matrix we have, real part has to be, I mean, okay, so let me clarify one thing that I can see is very confusing to you. The stability of a differential equation, right, du dt equal to lambda u, is very different from the stability of a iteration, right? A iteration that is, for example, u of k plus 1 is equal to a number times uk. For the iteration, for the differential equation, the stability criterion is that lambda has to have a negative real part. But for the iteration, right, uk plus 1 equal to, let's say, a times uk, the stability criterion is not a less than 1, right? I mean, if a is negative 2, we have seen in our case that we get an unstable solution. Every time you can imagine u gets multiplied by negative 2, so it becomes 1 minus 2 and then plus 4 and negative 8 and plus 16 negative 32. It's unstable, right? So it's not negative, but the magnitude of the coefficient has to be less than 1. And in this case, we get a matrix. I mean, what's the magnitude of a matrix?